Hey there, chemists. We're going to continue looking at how to match spectra of the NMR of certain molecules with known structures. But today we're going to broaden that a little bit and start to predict what we think we would see in the NMR from scratch, given a structure. And that'll set us up perfectly so that the next time we talk, we'll be able to go the other way and interpret a spectrum without knowing anything about the possibility of its structural architecture. Okay, so what we have here are 6 different compounds, and 4 of them have their spectra shown. So we're going to match which one goes with which, and then we are going to predict what the other 2 should look like based on splitting, integration, peak location, and number of signals, the 4 things that NMR tells us, which I reminded us of up here. So starting with spectrum A, the simplest one, it's a singlet. There's no relative integration. There's only one signal, so there's only one type of hydrogen, and that's it, one type of H. And if you look at the possibilities in the molecules, the only one that has enough symmetry to do this would be the cyclohexane molecule. Every single hydrogen is in the exact same chemical environment. It's also a good reminder of how splitting works. If you draw out some or even all of the hydrogens, you might say, wait, wouldn't these be split because they have neighbors? No, identical H's do not split each other. And those 2 are in the exact same chemical environment as what their neighboring hydrogens are in. So they don't split each other. Same reason that those 2 don't split each other on the same geminal carbon. So only if they're in different environments and adjacent do we see a splitting pattern. So A is cyclohexane. So we've taken care of one of them. Right below it, spectrum B, also very simple. We've got only 2 signals, but in a 1:3 ratio or a 3:9 ratio. That's actually enough to tell us which one it is. Just based on the number of hydrogens in the molecule, it must be this ether, because that has a 9 hydrogen tert-butyl group and a 3 hydrogen methyl group. So I'll draw it the other way around, and I'll even fill in some of the H's so we can make sense of how many there are and why there's no splitting and the location. The methoxy right there on the oxygen would be fairly to the left in the spectrum. It would be what's called de-shielded in the 3s and 4s because they're hydrogens attached to a carbon that's directly on an oxygen. Whereas these methyls on the tert-butyl group, notice they have no neighbors because that's the adjacent carbon, so it makes sense that it's a singlet. They're all in the same environment, so I get a 9 hydrogen signal, and it's fairly shielded. It's down in the alkyl region, so we would see just one signal on the right. And if you look at the other 2, the one in the lower right, we've actually seen this before. If you look back at your notes, I can recognize this from a couple of lessons ago. It's this epoxide up here. And it's because of the asymmetric carbons in this molecule that we see such a different splitting pattern. That one, actually the one asymmetric carbon, desymmetrizes the molecule, at least in the predicted spectrum. That's where this came from. These are predicted NMRs using a software called ChemDraw, but it's a good teaching exercise. We see a single signal for that hydrogen right in the middle, and that would be split into a multiplet. And then we see, if you remember talking about this before, all these doublets of doublets because of different splitting patterns in other parts of the molecule. I'm not going to go through and identify each one, that's most of them though, but it's simply because we've seen it before that it's fair to ask about it this time. I would not expect at this level of the class to be able to predict that, even we've seen that exact one before. And then if you look at the remaining choices, we've got a ketone and an ester, and then we have a much larger molecule with an asymmetric carbon and an alkene and lots of different types of hydrogens. That must be spectrum C, simply because it's so complicated. And a good exercise would be to go back and try to identify some of the H's that you can in this molecule, but it's worth simply saying it's very complicated compared to the others. This is actually a molecule that I made back in my days in grad school, one of the first homoallylic alcohols I had to produce for my starting materials. I recognize that OH, those vinylic hydrogens, There's the alcohol hydrogen right on the carbon, and then you've got your allylic hydrogens and the rest of your isopropyl group. But it's a complicated spectrum, and I can tell that it's not as simple as this ester or this ketone. So now our task is to identify, or predict rather, what would the spectrum look like for those other two. So let's redraw one of them first. Start with the ester and try to predict how many signals should we have, where would they be located, what would their relative integration be, and what would the splitting pattern be. So number of signals, splitting, location, and integration. Those are the 4 things that NMR will tell us. And we should be able to predict all of those now that we've done enough practice with this, given a particular structure. Let's start by actually drawing out all the hydrogens just to see them. There's 3 to the left of that carbonyl. There's 2 on the carbon directly attached to the oxygen, and 3 more all the way on the end. So the number of signals, just answer these questions, we can start to answer them a little bit. The number of signals should be 3, because there's 3 different types of signals. And then what should they be split into? Well, I'll write it next to each one. Let's simultaneously do the integration and the splitting together, because that's how we usually write them. So on the left, I would have a 3 hydrogen signal, because there's 3 of them. And if you look at the adjacent carbon, there's 0 hydrogens. So this should be a 3 hydrogen singlet, so 3HS. In the middle, these 2 H's, they would integrate for 2, so this is a 2 hydrogen signal, and they have 3 neighbors, so they should be split into 4, so that would be a 2 hydrogen quartet. Lastly, these 3 hydrogens would be a 3 hydrogen signal, and they would be split by the 2 hydrogen neighbors into a triplet. Remember, it's always the number of neighbors plus 1 to get the splitting pattern. So 2 neighbors becomes a triplet, and 3 neighbors becomes a quartet. So that takes care of everything except for the location. Where's the location of each of these? Well, we can look at this and try to predict who's the most electron poor. That would be the 2 hydrogen quartet, because it's on a carbon next to an oxygen. And our scale predicts that that would be somewhere near 3s and 4s. So I would guess that we would have a 2 hydrogen quartet somewhere in the 3s and 4s. And I'm going to draw it just as a sequence of lines. 1, 2, and then a quartet has shouldering peaks that are actually only a third of the area of the interiors. We're just going to draw them as lines, and we'll label it 2H quartet. After that, we've got the 2 3 hydrogen signals. The one next to the carbonyl would most likely be the next electron poor, probably in the 2s if you look back at any of those reference charts we've been looking at. And it should just be a singlet, and it should be worth more. This was 2, so relative to this signal, it should integrate for more, and I'm going to indicate that by drawing it a lot taller, because it's also an area distributed among just a singlet. Remember, integration is not peak height, but peak area. But height gives us a general sense of what the area is. And then lastly, the least electron poor hydrogens would be the triplet, probably down in the 1s somewhere. And it would also be 3 hydrogens. Since it's a triplet, since it's split, the area would be the same, but the height would be less than our singlet. So I'll draw a rough approximation of a triplet, probably in the 1s somewhere. And it's going to be in a 1:2 to 1 ratio of areas of those peaks. That's your 3 hydrogen triplet. And then we can predict, or I should say label which one is which. Our singlet out there corresponds to that signal. Our quartet in the middle is that signal. And then our triplet on the right corresponds to that signal. So now we have one more molecule to predict. Go ahead and hit pause, and this time try to predict an NMR for that ketone. Okay, the first thing I would do is actually draw in the hydrogens. There's 3 on the left. There's 2 right next to the ketone, 2 beyond that, and then 3 more all the way to the right. And if I created a peak list off to the left, I would have a 3 hydrogen singlet, because it integrates for 3 but has 0 neighbors. And then I would have a 2 hydrogen signal split by these 2 neighbors, so that would be a 2 hydrogen triplet. I would then have another 2 hydrogen signal, but split by these 3 and these 2, so potentially 5 plus 1 into a sextet, in other words, 6, multiplet of 6 different peaks. And then lastly, a 3 hydrogen signal split by these 2 into a triplet. And the location of this, not many of them are very electron poor. The only electron poor hydrogens we have are these signals that are next to the ketone, and they're not even that electron poor. They're alpha to a ketone. That's probably in the 2s, so I'd predict that those would be somewhere in the 2s, so rather far to the right. We'd have a triplet and then a singlet, probably right near each other. In fact, it's hard to predict exactly what order those would be, and it's possible those could be switched because they're in such similar chemical environments. The triplet is attached to more carbons, but this actually turns out to be what it is. But if you flipped these 2, I would give you full credit for it at this stage of the course, because that's really hard to predict. So those 3 hydrogens would be the singlet, and then those 2 hydrogens would be the triplet. And then we get to even less electron poor atoms. Now we're getting to the 2 hydrogen multiplet, or sextet in this case. That's going to be even less electron poor, probably in the 1s. Now to draw a sextet and make it worth 2 hydrogens, I want to have it integrate for the same as this, but it's split more than triplet, so it's going to be shorter. And since it's split into an even number, a sextet, you know it's always going to be a central pair of peaks surrounded by shouldering peaks in an even ratio, maybe something like that. Maybe that is what our sextet would be. And then lastly, we have our triplet, which is 3 hydrogens. So we'll show a 3 hydrogen triplet, even more to the right, probably down in the 1 or even below 1 range. So just a rough approximation of where that could be. Our last 2 signals. So it would probably be a very crowded spectrum because it's so shielded, so electron rich compared to things like the ester up above. So there might certainly be some overlap of these signals, but that's a good way of predicting what the NMR would look like for those 2 compounds.